Hello. Today we will continue with public key cryptosystem, which is the most famous one, RSA. First of all, I will today what we are going to I list what we are going to do today. I will make a brief introduction of public key cryptosystem. Then I will explain what RSA is, what is encryption, what is decryption, what is key generation in RSA. Then I will briefly mention the security of this scheme. And the rest of the lecture will include fast exponentiation, which is secure square and multiply algorithm in order to make exponentiation faster. And finally, for RSA, we need big primes. We will see it later. And we need some tests in order to check whether a number is prime or not. So we call them primality tests. We will see some of them today. Now let's start what we have done before. We saw until now symmetric key crypto. It's like this. We have an encryption scheme, and there is a insecure channel. And there is a decryption algorithm, and we have plain text, which is encrypted with a secret key, and we obtain ciphertext and we send it through an insecure channel which is an encrypted value, so no one can see it. And we obtain Y here with ciphertext, and there's a decryption function, and the same key is used in order to obtain the plain text. We say this Alice, and this is Bob. Alice sends this text by encrypting with the key, with a secret key, and Bob decrypted with the same key. This is why we say it is symmetric. Same key is used for both encryption and decryption, and the key has to be sent in a secure channel. This is important. And if we have a lot of users and they need to communicate with each other, so we need them to share this secret keys in a secure channel, and which is a real mess by doing this with a symmetric key cryptography. Until officially in 1977, there was always symmetric key until. After those, symmetric key cryptosystems are invented. So what is asymmetric key cryptosystems? Assume that we have two users as before, Alice and Bob. But in this case, Bob has two keys. One is public key, the other key is secret key. The public key is a key that Bob can distribute to other people, or distribute it through its website or something that people knows it. It's public, it's known key. And he sent this key, KPK, to Alice. Now, assume that Alice wants to send a message to Bob, and Alice encrypt the message with the public key of APK of Bob and assume that this is maybe it's a file or email or something secret, and obtain the ciphertext and send the ciphertext to Bob. And Bob can decrypt it with his secret key or private key. The notations can be confusing. Maybe I can make it SK. Obtain the plain text. So what is important here? In asymmetric key cryptosystems, everybody who has Bob's public key can encrypt. However, this is important. However, only Bob can decrypt. When a plaintext is encrypted with a public key of a public key cryptosystem, only the decryption function works for the secret key of this corresponding public key, which is usually owned by the owner of this key. As I said that, I'm repeating. Everybody can encrypt the message and send to Bob with its public key, but only Bob can open the message by its secret key. So this is the idea of asymmetric key. In encryption and decryption, the keys are different, but they are mathematically related. We will see it later in RSA. Okay, but what is important here? Okay, we understand the encryption. So what is this encryption function? These are important, right? In order to satisfy these properties. So let's move to RSA now. After seeing the general structure of asymmetric key crypto, RSA is designed in 1977 by Rivest, Shamir, and Edleman. It was patented in the US until 2000, but still it is used, and it's, I think, the most popular public key crypto system. It is the short for public key crypto systems. I will not write, from now on I will write PKC. And this is like DES and AES, so it is such a popular, everybody, when somebody says asymmetric crypto, and you have to remember that there is RSA, which is the first encryption with asymmetric crypto. So let's see what RSA is. So I remember I said this before, that asymmetric crypto includes more map than symmetric crypto, because of course of symmetric crypto there is mathematical background when you are designing a block cipher, but here when generating the keys, when encryption and when doing encryption and decryption, you need more math. RSA is also asymmetric crypto. So that's why we have seen last week some number theory for to get ready to understand RSA. And also, since it's asymmetric crypto, we need to generate two keys: public key, let's say PK, and SK. I'm changing notation now, it's easier for me. So here, key generation. So how do we generate the keys for RSA? It is first we choose large primes P and Q, and we multiply these two primes. These are primes. Usually we denote primes P, and the other prime we denote with Q. This is always this case. I mean, when you say that P and Q in RSA, they are prime. So we multiply P and Q and we obtain N. Then phi of N is PQ minus 1. This is Euler phi function. We have seen it last week. And maybe I should numerate this. This is 1, 2, 3, and 4. And we choose a public key, PK, with, don't confuse. We choose a number E in between 1 and phi n minus 1, such that GCD E of phi of n equals to 1. So you know that always there is a reason in order to choose this, because we need E has an inverse E. And the fifth, we compute D such that D times E is equal to 1 modulo phi of n. So here, in fact, D is an inverse of E modulo phi of n. You know that if an element is an inverse, then if you multiply it with this element, then you get 1. So this means that D is an inverse of E, or E is an inverse of D. So that's why we choose that the GCD of E and phi of n is equal to 1. So here, this is important that the public key, maybe let's say PK, is equal to N and E. This number N, which is P times Q, is public, and K secret key is D. D is the secret key, public key, and E. Of course, these primes P and Q's are also secret. So let me make a remark. is if P and Q is more than equals like 2 is bigger than equal to 2, 5, and 2. This means that it is like 512 bits long. And N will be around this. This means that it is around bits long. And normally now if N is larger, if N is larger for RSA, then it is more secure. It is more secure. So the security of RSA depends on the bits of N and P and Q, of course. If it is shorter, then it is. If it is, for example, N is 512 bits, then it's not secure anymore. So even in most of the application, previously we were using 1024 bits for N and the key size for RSA, but we start using 2048 bits in order to make RSA more secure these days. So longer key bits provides more security in RSA. So also the extended Euclidean algorithm, this is remark 1 and 2, extended Euclidean algorithm is used to compute D. So that's why we need extended Euclidean algorithm in RSA. Okay, let's see how we do encryption. In order to make encryption, we assume that we are given public key, which is N and E, and we have a plain text, which is chosen in Zn. You know that what is Zn, 0, 1, up to N minus 1. And the encryption function is pk, is encrypted, which is, this is the plain text, ciphertext, and x is the plain text, x to the power e modulo n. That's it. This is the encryption. We just take the exponentiation of x to the power e in modulo n. And decryption, now in order to decrypt, we are given the secret key, which is D. Of course, we are given also N, and this we have the ciphertext. In order to get the plain text, we have a decryption function with sk. Sorry, we decrypt the ciphertext, and we make y to the power d modulo n. So this is the decryption function you need to know for RSA. This is encryption and decryption. It's very simple. These are important. Let's make an example. I will just make a simple encryption and decryption, of course. We have Alice and Bob. Now we assume that Bob has private key and public key. Now let's generate it first. And what was the steps? He chooses two prime numbers. Let's say P is 3, Q is 11. And the second, what was it? P times Q, which is N. Let's compute N, which is 33. And the third one, we were computing phi of N, which is phi of 33. We know that this is P minus 1 times Q minus 1. This is 3 minus 1 times 11 minus 1, which is 20. And the fourth step, we choose a public key. Let's choose 3. It can be same with this P, doesn't matter. Which is E. What was important that E and phi of N, 20, has to greatest common divisor GCD of 20 and 3 has to be 1. So this satisfies. So this E is true. And we compute, as the fifth step, we compute D, which is an inverse of E minus 1. So this is 7 modulo phi. This is important that we need to invert E, according to modulo phi of N. It's not modulo N. This is important in key generation. You have to be careful. Okay, now we know that E is 3, D is 7, N is 33. Now Bob can send its public key to Alice, which is PK was 33, N and E. This is N and E. Now Alice can encrypt some text to send Bob. So Y is, assume that Alice pick X is equal to 4 to the power 3, which is E, which is 64 modulo 33, which is 31, and Y, send Y to Bob, and Bob, in order to find X, Bob compute Y to the power 7, because only Bob knows this, which is 31 to the power 7 modulo 33. This is important, which is 4 modulo 33. So here, in order to compute this X31, you can always do some tricks. For example, here minus 31 is equals to minus 2 in modulo 33. Now this is easier to compute this. You don't need a calculator to do this. So in these exponentiations, you can always some tricks to do, also in exams. So this is how we compute encryption. First, we make key generation. We choose two prime numbers. We multiply it in order to find N. We compute phi of N. We compute E, which is relatively prime to phi of N. Now we compute D according to modulo phi of N. Bob sends its public key to Alice. It's not normally in this way in real life, but this is just an example. And then Alice wants to encrypt this message, use Bob's public key to encrypt it and send the ciphertext to Bob. And as Bob has know his secret key, and make the power of 7, which is a secret key, and obtain 4. So in fact, the correctness of RSA encryption and decryption, how we obtain X through this here, how we obtain this. I would not go that much detail, but it's an exercise for you. It's to learn. If you are curious about why it works, it's in the book I think in page this understanding cryptography book. Our course book, Understanding Cryptography. If you are curious about why RSA works, it's related to Fermat's Liddell theorem. The proof is based on this theorem. If you are curious, and if you have questions, you can ask me through an email if you don't understand it, but I won't go that much detail for this course. So we are now moving to the security of RSA. The security of RSA is based on hardness of factoring. So here, when we have a look at the scheme, so what is important here that in order to compute, the secret key, which is D, if we know E and if we know phi of n, we can easily compute D by extended Euclidean algorithm as Bob does. But in order for RSA to be secure, this phi of n has to be has to generate. We cannot generate phi of n easily. So what was the phi of n? In order to generate phi of n, we need to know P and Q, so which is n PQ. N is P times Q. We know n, but we don't know P and Q. So the problem here that the attacker or Alice or anyone cannot factorize n into primes. So normally in math, it's a hard problem. If you have a big number like 1000 bits or more or a bit less, if you have big primes, if n is a multiplication of 2 big primes, it's not easy to it's not doable to do it in a polynomial time. So this is what we define as hard problem. So the security of RSA is based on the hardness of factoring. If we can factorize a big number into 2 prime numbers, we can break RSA. We can easily compute the secret key. As this factoring is not easy, is not doable in a polynomial time, so RSA is provable secure scheme, because there is no such an efficient algorithm to factor n. So this is the security of RSA, which is based on. There are problems and there are more things. Of course, there is more things, but I will skip those parts. It's not the topic of this course. But you have to know that the security of RSA is relying on the security of factoring problem, hardness of the factoring problem. So let's move to the fast exponentiation. Fast exponentiation. Let's start with an example. Let's compute x to the power 8. Now we can do it by multiplying, like multiply x by x itself. Multiply with, this is multiply with x, we obtain x squared. Multiply with x, we obtain x cube. Multiply, we obtain x4. Multiply x5. Multiply x6. Multiply x7. Multiply x to the power 8. So here we have 7 multiplication to get 8 to the power 8, x to the power 8. So when we do by squaring, obtain x to the power 8 from x by using squaring, square each time. As we denote that by sq, we obtain x squared, and we square this, we obtain x to the power 4, and we square this, obtain x to the power 8. So here we use 3 squares. When using multiplication, we have 7. When using squaring, we have 3. So here, as you said that when we use squaring, we have less operations. Squaring is less than multiplication, the number of squaring. But of course, the complexities are different, but I won't go to complexity now. By using multiplication and squaring, multiplying and squaring, we have a square and multiply algorithm. I will show you through an example. Let's compute x to the power 26 through this algorithm by square and multiply algorithm. Here, first we write 26 into base 2, which is 1, 1, 0, 1, 0. This is 2 to the power 1, 2, 3. This is 8, this is 16, and we have 26. And let's write it with unknown. These are h, h3, h2, h1, and h0. In order to do this algorithm, we start from h4 to h0. So these steps of this, the step 0, we start with x. Okay, this is x to the power 1. And the step 1, in this algorithm, we always first square, then if it is necessary, we multiply. I will show you why. Here I square it, this x1, I square it, which is x squared. When I write in base 2, this is x1, 0. As I said that I start from h4, this was h4, This has to be always 1 because there is no reason to write zeros here. This is H4, this is H4, and this is H3. And 0, here, here H3 is, let me write H1 and H0. H3 is 1. So if it is 1 here, we need to make one multiplication. So in this is step A and step B, I need to do one multiplication with x, and this is x cube, which is x11. Now I am done with H4 and H3. And step 2, A and B. Here, as I said that in every step, I have to do one squaring. So I need to square this. Which is this. As H2 is 0, this is, you know that this is H2, so I don't need a multiplication. So I won't do any multiplication here because I already obtained 0 here. If I do multiplication, this will be 1, but here it is 0, so it's not necessary. And in step 3, A, I need to do one squaring, which is 212. This is x to the power 1, 1, 0, 0. In fact, when you do one squaring, this is shifted by 1 and you put 0 here. It's very easy. I don't do anything, just put 0 here. And what was small it. Here I am in H1. H1 is 1, so I need to make one multiplication in order to put 1 here. It's x13, which is x1101. So I obtain H1 here. And the last step for H0, of course, I will make for first squaring x26. This is what I in fact want. And this is now I'm done. I do this in 4 steps. Let me write the pseudocode and I explain it once more. Basically, we scan the exponent bits left to right, as I said that it was before H4 to H0. Then in every iteration, we always square in every step, but if the current bit is one of these HI is 1, then we multiply by x. Now I suggest you to compute by square and multiply algorithm. This is just exercise, it's not homework. Now we are done with this fast exponentiation. Now let's move to the prime numbers to generate big prime numbers. So there are some tests in order to generate prime numbers. In this course, I will mention Fermat test and Miller-Rabin test. So in this prime numbers test, the test always says that when a number is not prime, first of all, when a number is not prime, we call it composite. So here this test, usually in prime test, they either output the number is composite or it is likely a prime, likely prime. So it's 100 for 100% it says composite, but for some probability, it's like because we make iteration such that the test the probability is so high that it is likely a prime. There is always a possibility that the number is not prime. So this is how this primality test works. So let's start with the Fermat test. So this is based on Fermat's Little theorem. We have seen last week. So the input of this test, the input, and there's output, and the input is a prime. This might be a prime. It's a number, and S, which is a security parameter, and we will see it later. What is this S? How is it used in the algorithm? And the output is P is composite, it's not prime, or P is likely prime. And the algorithm is like this. We choose an element in every iteration. This is one iteration. Choose an element A from set which is smaller than P. Then compute P minus 1, whether it is modulo P. This was, this was the Fermat's Little theorem. If it is not 1, so we said that it is not a prime because it works for every prime. For every prime number, a to the p minus 1 is equal to 1, right? So this means that p is not prime, or it is composite number. And we do this S times. We repeat this algorithm every time we choose a new A, and we do this algorithm S times in order to make the complexity, this likely prime is high. And then if it passes, if for every A, if it is 1, then we return that P prime is likely prime. So as I said that if it is not prime, for 100% the algorithm output the P is not prime, or P is composite. But with some probability we run these algorithms like S times, maybe 100 times or 80 times or 50 times, and we return that P is likely prime. But there is a problem in this algorithm because there are, maybe you know these numbers, there are spatial numbers. This is important. Sorry. There are spatial numbers which satisfy a to the power c minus 1, 1 modulo c. So these numbers are Carmi numbers. So they are not prime. These numbers are not prime, but still satisfy this. We call them as Carmi-Hall numbers. So these numbers are not, there are many when you consider big numbers. So there are many Carmi-Hall numbers. Therefore, as there are many Carmi-Hall numbers which behaves like primes, but they are not prime numbers, which passes Fermat test, although they are not prime. This Fermat test are not used in practice.